Hello, this is section 4.5, integration by substitution. So pattern recognition. In this section, you will study technique for the integration composite functions. So discussion is split into two parts. One is a pattern recognition and then change the variable. And then both techniques involve the use substitution. So with the pattern recognition, you perform the substitution mentally. And then with the change of variable, you will write the substitution step. The role of the substitution integration is compatible to the chain rules in the differentiation. So we call that for the differentiable functions, y equal to f of u and u equal to g of x, and then we'll get that the form of this one. All right, so we get that out for those. Okay, so this is what we need to remember for the integration as the pattern recognition. So when you see as the f function is outside function, g of x is inside function, and then g prime of x is differentiate for the inside function. So in number one, what I have in here, which is I just need to recognize that if I say let g of x is x squared plus 1 and g prime of x is 2x. So this is actually the form of f of g of x, which is f of x squared plus 1, and then you plug it into the x squared plus 1 square. So from this, you can recognize that the integral follow the f of g of x times g prime of x pattern. So if I'm using power rule of the integration, then I have integral x squared plus 1 square of 2x dx, and then I get the 1/3 of x squared plus 1 cubed plus c. Because I want to say this whole thing is f of g of x, and then this is g prime of x, and then dx. So try using the chain rule to check that the derivative of the 1/3 of x squared plus 1 cubed plus c is integrand of the original integral. So recognizing pattern, so is from the a to c fits the pattern of the f of g of x times g prime of x, and then the d in f is also similar to the a to c. Show how to you can multiply divide to constant to find the integral. Okay. So integrand in example 1 fits the f of g of x times g prime of x, and the pattern exactly. You only have to recognize the pattern. So you can extend this technique considerably with the constant multiple rules. So k is a constant, you can also pull it out too. Alright, so let's try this one. So if you recognize it, so since we have if you say g of x is x squared plus 1 and g prime of x should be the 2x, but I don't see 2 from here. So what I can do is I want a little bit manipulate, okay? So the integral of square of half times, now I got 2x dx. So in order to do that, I can pull it out the 1/2 of, because this cancels out to go back to the original problem, right? So you got the x squared plus 1 square and 2x dx. Then I can have a 1/2 of, and then this whole thing becomes x squared plus 1 cubed over 3 and plus c, and then you got 1/6 of x squared plus 1 cubed plus c. Okay, all right. So and then also the change of the variable for the definite integral. So if you have integration to find out this one, so this time I want to use the substitutions. So let's say u is 2x minus 1, which is a u prime is 2 dx. So for u prime, instead of the u prime, I want to say du, okay? So du is, and then du over 2, which is same as a dx. Okay, so what I do is integral and the square of u, and instead of the dx, I use a du over 2, and then pull out the half of square of u du, and then square of u same as u to the half power du, and then I can use a power rule, which is 1/2 plus 1 over u to the 1/2 plus 1 plus c, and then I got 1/2 of and 3 over 2 over u to the 3 over, oh sorry, what am I doing? I'm messing it up, sorry about that. Over here, and then I got integral, what am I, no, what am I doing? From here, I just need to do u to the half plus 1 over half plus 1, and then half of, you got u to the 3 over 2 power over 3 over 2 plus c, and then half of, and then you multiply by reciprocal, it's going to be the 2/3 with u to the 3 over 2 plus c, and then it's going to be 1/3, and then we can put it back to the original, which is u was 2x minus 1 cubed and plus c. Alright, so that's finishing the antiderivative, okay? Alright, so got the line for the making a change of variable. Number 1, choose a substitution u equal to g of x, and usually it is best to choose the inner parts of the composite function, and such as a quantity raised to a power. Compute the du equal to g prime of dx, and rewrite the integral in terms of the variable u. And number 4, find the resulting integral in terms of u. Number 5, replace u by the g of x to obtain the antiderivative in terms of x, and check your answer by differentiating. So general power rule for the integration, one of the most common u substitution involve the quantities in the integrand that are the raised to a power. So because of the importance of this type of the substitution, it is given of the special name. So we call the general power rule for the integration. So yeah, we gotta use this. Okay, so I put down some the popular ones we might need to see as here. So try to take a look at what happened here. And change of the variable for the definite integral. So when using a u substitution with the definite integral, it is often convenient to determine the limit of the integration for the variable u rather than to convert the antiderivative back to the variable x and evaluate at the original limit. So this change of the variable is stated explicitly in the next theorem. So change of the variable in definite integral, and then we'll get this form. Alrighty, so number 4. So in order to evaluate this, I want to say u is x squared plus 1, so the u is 2x dx, and then du over 2 is the same as dx. So what I do here, I use 0 to 1. And also, yeah, we're converting to the u, so let's put it this way first, okay? So in order to do that, I want to say, because of here, so when x equal to 0, and then u is going to be 1, and then x equal to 1, because of that, plug it in, u equal to 2. So you can change that as 0 to 1. Instead of the 0 to 1, you can say integral from 1 to 2 of x times, now put u, times dx is the du over 2. 2x. What am I doing here? It's a 2x. And then the x's cancels out, and then this becomes the integral 1 and 2, and then u 1/2, pull it out, okay, and du, and then use a power rule, and then you got u cubed over 3 from the 0 to 2, the 1 to 2, sorry, and then half, plug it in, 2, so you got, what am I doing? Did I say u? Wasn't it? U cubed? Oh, sorry, u cubed, right? So u cubed, which is u to the 4, and this is a 4. Sorry about that. So u to the 4, which is u to the 4. So plug it in. So 8 over 4, subtract 1 over 4. And then you get the half of, and 5 over, on the 7 over 4. Okay, because u to the 4. Sorry, it's 16. 16. So that becomes, yeah, messing it up. Sorry about that. So 15. Okay. So you got 15 over 4, and then you got 15 over 8. So that is actually the integration for this, okay? So integration for the even and odd functions. So even function means you just need to getting twice of the area. And the odd function means you got that as area, but one is above and below, and then the area also cancels out as a 0. So the integration of the even and odd functions, so let f be the integrable on the close from the negative a to a. Okay, do you see that here? All right, so and then the even function becomes twice of it, and then the odd function is actually the becomes a 0. Okay, so when you actually the graphing this, you'll see the graph of this one. So this must be odd functions. So odd function, because odd function, it must be equal to the 0. Okay, but I want to actually this function is odd function or even function in here. Okay, so in order to find it, which is f of x is sine cube x cosine x plus sine x cosine x. And the f of negative x is sine cube of negative x cosine negative x and plus sine of negative x and cosine negative x. So if I do it, cosine is always positive, so negative sine cube x and cosine x. Because of the sine, it's going to be negative sine x and then cosine x, which is the same as negative f of x. So that's why it is an odd function. So odd function, we expect it as a 0, as integration, as a definite integral. Okay? All right. Thank you for listening.